Now, chapter 12, exercise 12.1. Choose the correct alternative from the clues given at the end of each statement. A. The size of the atom in Thomson's model is blank the atomic size in Rutherford's model. So options: much greater than, no different from, much less than. So it is no different from. Atomic size was established, radius of the order of 10 raised to minus 10 meter. So we have to give answer no different from. B. In ground state of blank, electrons are in stable equilibrium, while in blank, electrons always experience a net force. Options: Thomson's model or Rutherford's model. So in first blank here we have to take Thomson's model. So we can say in the ground state of Thomson's models, electrons are in stable equilibrium. Because in that we considered this thing, entire positive charge is uniformly distributed in the atom and electrons are embedded in it. So it will be in stable equilibrium. From all the directions, the force will be balanced. While in Rutherford's model, electrons always experience a net force because in Rutherford's model, the entire positive charge is at the center in the nucleus and electrons are revolving around it. It implies that definitely there will be some net force which will provide the required centripetal, then and then only the motion will be sustained. C. A classical atom based on blank is doomed to collapse in Thomson's model or Rutherford's model. So answer is Rutherford's model. A classical atom based on Rutherford's model is doomed to collapse. We already discussed in the theory. If electron is revolving around the nucleus, then continuously it will emit the energy and move on a spiral path, and finally it will be at rest in the nucleus. D. An atom has a nearly continuous mass distribution in blank but has a highly non-uniform mass distribution inward. So an atom has a nearly continuous mass distribution in a Thomson's model, because in that we consider the entire positive charge is uniformly distributed and electrons are embedded in it. It implies that mass distribution is continuous in the entire atom. But in Rutherford's model, we discussed this thing, almost entire mass is concentrated at the center. So, but has a highly non-uniform mass distribution, that is in Rutherford's model. Clear? એટલે ફર્સ્ટ બ્લેન્કમાં આપણે થોમ્સન્સ લખવાનું, સેકન્ડમાં રુધરફર્ડ્સ મોડેલ. E. The positively charged part of the atom possesses most of the mass in what? Rutherford's model or both the models. So it is in both the models. Clear to all of you? 12.2. Suppose you are given a chance to repeat the alpha particle scattering experiment using a thin sheet solid hydrogen in place of the gold foil. Hydrogen is a solid at temperature below 14 K. What result do you expect? So suppose we take the solid hydrogen sheet and we bombard the alpha particle on it. Then for all those alpha particles which have large impact parameter, means the perpendicular distance of the velocity is large compared to the position of nucleus, or we can say atom. Then scattering, that will be very less. એટલે એ કેસમાં આપણને કોઈ ચેન્જીસ નહીં દેખાય. But if impact parameter is very small, કોઈ કેસમાં આપણે head on collision માનો કે લઈ લઈએ, but the results will not be like the scattering of alpha particle from gold, because hydrogen is very small atom અને એના ન્યુક્લિયસમાં એક જ પ્રોટોન છે. So it will not be able to exert the large force on alpha particle. એટલે આપણને સ્કેટરિંગ જે છે એ હાર્ડલી બહુ જ મામૂલી એંગલ ઉપર મળે તો મળે, રાઈટ? 12.3. What is the shortest wavelength present in the Paschen series of spectral lines? See, Paschen series given to you. So the base orbit for Paschen series, that is third one, n equal to 3. So for Paschen series, we can write the equation 1 upon lambda, that is equal to r into 1 upon 3 square minus 1 upon n square. And we want the shortest wavelength. So we already studied this thing. When the first transition we consider n equal to 4 to n equal to 3, then the wavelength will be maximum 1. But if we take the transition from 5 to 3, 6 to 3, 7 to 3, then continuously the wavelengths are decreasing 1. It implies that for the shortest wavelength, we can consider the transition from n equal to infinity to third one. So here in this particular equation, if we substitute n equal to infinite, then we will get the shortest wavelength of Paschen series. So we can write 1 upon lambda, r that is 1.097 into 10 raised to 7 into 1 upon 3 square minus 1 upon infinite square. So this one will be 0. 1 upon 3 square, that is 1 by 9, r as it is. And now solve this one, you will get shortest wavelength of Paschen series. Clear to all of you? 12.4. A difference of 2.3 electron volts separates two energy levels in an atom. What is the frequency of radiation emitted when the atom make a transition from the upper level to the lower level? So here, the energy difference between these two levels, that is given to you 2.3 electron volt. So during this transition, if this much energy is emitted in the form of radiation, and if the frequency of the emitted radiation is f, then this energy E, which is 2.3 electron volt, we can write that is E equal to HF. So F equal to E by H. Now substitute the values. E 2.3 electron volts, so multiply it by 1.6 into 10 raised to minus 19 and then divide by 6.625 into 10 raised to minus 34. Solve this one, you will get the frequency of the emitted radiation. Then after 12.5, the ground state energy of hydrogen atom is minus 13.6 electron volt. What are the kinetic and potential energies of the electron in this state? So total energy, that is minus 13.6 electron volt. Now kinetic energy, that is equal to minus E. So that is equal to minus 13.6, you will get that is plus 13.6 electron volt. And potential energy, that is twice the total energy. So 2 into minus 13.6 equal to minus 27.2 electron volt. Simple example, clear to all of you. 12.6. A hydrogen atom initially in the ground level absorbs a photon which excites into the n equal to 4 level. Determine the wavelength and frequency of the photon. Okay. Now see, we have the equation for the energy in nth level, that is minus 13.6 upon n square electron volt. So in ground level first, calculate the energy. E1, that is minus 13.6 upon 1 square, that is minus 13.6 electron volt. Then calculate the energy in n equal to 4 level. So that is equal to minus 13.6 upon 4 square. It will come to minus 0.85 electron volt. Now say, initially in the ground state absorb a photon and excite to n equal to 4. Now from excited state it will jump to ground state again. So the amount of energy emitted, that is the difference of these two energies. So delta E, that is equal to E4 minus E1, that is minus 0.85 minus minus 13.6. So it will come to 12.75 electron volt. And now we can write the energy of the photon, that is equal to HF. So F equal to delta E by H, delta E, that is 12.75 electron volts. So multiply it by 1.6 into 10 raised to minus 19. So it is in joule, and then substitute this value of H, solve it, you will get the frequency. Now lambda, the wavelength, that is C by F. Substitute the value of C, 3 into 10 raised to 8, and F, which we calculated here, and then solve, you will get the wavelength of the photon. Clear?